I know you are very excited to start this lecture, so it's not true, is it? Okay. As usual, before we start the new lecture, I would like to look back at what we covered last week. This lecture will talk about multicollinearity and heteroskedasticity. These are the topics we will cover. We covered already 2 topics, and today we'll move to the 3rd topic, multicollinearity and heteroskedasticity. So, as I said before, we make some assumptions about the regression model, and we need to test for the validity of these assumptions, whether these assumptions are true or not. So the lecture today will be related to assumption 6 and assumption 4. So no multicollinearity, assumption 6, which means no perfect linear relationship among the x's or the regressors. So this is an assumption. Then we need to see how to make sure that this assumption is true, and what if it is not, what should we do? Okay? Then we'll move to talk about assumption 4, which is related to the variance of the error term. We assume that the variance of the error term is constant. Then how can we test whether it is constant or not? What are the implications if it wasn't constant? Then how can we remedy for that? How can we correct that? So these are the 2 points or the 2 assumptions that we will be dealing with today. But before we start, let's have a look back to the lecture last week. What we covered, we talked about including qualitative information into your regression, and we said that could be the case on the right-hand side. So meaning that there are some qualitative measures or information that you wish to include as one of your regressors or one of your x's, so it's on the right hand side. We call this dummy variable. So we try to define a dummy variable, and things like gender, for example, or maybe if you talk about seasonal effect or whatever, so something you want to capture by a dummy variable. So talking about a dummy variable as an example, if we want to see how gender can be one of the factors that determine, let's say, wage, then we define a dummy variable that, let's say, called female. So we give it 2 values. If the person is a female, it takes 1, otherwise it will take 0. And we explain how to interpret the estimated coefficient in that case, and the coefficient that is attached to this dummy, okay, that would be the difference between, so you compare with or compared with the reference group. So your reference group always going to be the group that you assign 0 to. Okay, so remember we give or the way we defined female as a dummy variable, it takes 1 if the individual is a female and 0 if the individual is a male. So that means male here is my reference group, or the group I'm comparing with. Call it a benchmark group, call it whatever you want, but this is, at the end of the day, this is the group that we compare with. So the estimated coefficient in this case, that's attached to this female dummy, the way we define it, as we explain now, explain the difference between female and male, and if the sign is positive, that means female earn more than male, given that they have the same characteristic, the other characteristics, education or whatever you controlled for in your equation. So 2 individuals with the same characteristics, they will earn differently, and that depending on how much is the magnitude of that coefficient and also the sign. So if the sign is positive, that means female earn more. If the sign is negative, that means females earn less. And again, these are on average. So, and then we move to, we'll also explain how we could actually have interaction terms between these dummies. If you, we had an example where we had a number of dummy variables, not just female. We talked about whether the person is a member in a trade union or not, whether the person is ethnicity as well. We had another dummy variable for ethnicity, etc. And we explained that you could actually have some interaction between these variables. And always think of what is your reference group, because before you try to interpret an estimated coefficient from to a dummy variable, then you need to first ask yourself how this dummy variable is defined. What is my reference group? Which group I'm actually comparing with? Then this was the first half of the lecture, and then we moved to talk about in the second half. We explained a case where we actually have this sort of dummy variable style in the left-hand side, not actually in the right-hand side. So the qualitative information that we want to model, actually in the left-hand side, it's your dependent variable. So in a dependent variable, we said if we have a dependent variable that takes only two values, 1 or 0, yes or no, then, and we estimate this model using OLS, ordinary least square. So this model in this case called a limited dependent variable or linear probability model. Linear probability model, because we said the way we interpret these coefficients, the estimated coefficient is actually probability. Okay, so it's the probability of success or the probability that this whatever you model will happen, or yes, or it takes value of 1. We explained that there are other models that actually can estimate this model, and there are other cases where you can actually, your dependent variable can take more than 2 values, so it's still restricted, but it's not as restricted as 2 values. But we said these are not covered in this module. So these cases are not covered in this module. So for example, nonlinear estimation of the same model where your dependent variable takes only 2 values, 1 or 0, we could use logit or Prophet model, and said these models were not covering in this model. So the simplest way to model a variable, okay, or to estimate an equation where your dependent variable takes only 2 values, 1 or 0, is using OLS. But then you need to understand how can I interpret the betas or beta hat or the estimated coefficient in that case. These are your probability, and that's why it's called linear probability model. And then we finish the lecture, we conclude the lecture by highlighting the limitation of this sort of modeling technique, the linear probability model. And we explain one of the main issue with this is that probability should be should take the value from 0 to 1, and with a linear probability model, or with this all estimation of this model, there's nothing to guarantee that this will be the case. Okay, and we explain other limitation as well. So this is everything we covered last lecture. So if you just think of this as a takeaway message, or it's things that you should have picked up from the previous lecture. Today's lecture, the lecture is in Hanomics. So the previous lecture, the last week lecture 7, it's recorded and it's now in Hanomics. You can follow the recording by just click on that link. That should take you straight to the lecture. And as I said before, feel free to subscribe so you can get notification once I upload a new content, so you don't have to wait until I notify you that there is actually a video on Hanomics. So as I said today, we will talk about two topics. One is multicollinearity, and the other one is heteroskedasticity. And as I said, these are related to the assumptions that we made about the regression model. So one assumption was assumption 6. We assumed, or we hope that there's no linear or exact linear relationship between any two x's or any of your two variables on the right hand side, your regressors. So and in any case that we have, I mean, we have two cases when you have perfect multicollinearity. So what if this is not true? So what if there are two or more variables that are actually collinear, or there's some sort of linear relationship between two or more variables in the right hand side? So we differentiate between these two cases when you have perfect multicollinearity and you have imperfect multicollinearity. So perfect multicollinearity is something very rare. So you're not going to find this usual or very often in your in a real situation, because this is usually a specification error. So it sometimes it happens because you don't have the right specification or the correct specification. And one example we gave actually last week when we talk about a very common example of perfect multicollinearity, when you, for example, have, let's say, a dummy variable for gender. And if you remember from last time, we said if you have two groups, then your dummies, or the number of dummies you include in the model, should be how many? So if I have two groups, exactly. So if I have four groups, how many dummies? 3. So it's all G minus 1. So you drop 1 because this is your reference group. This is the group you compare with. Given that you have an intercept. So given that you have beta naught, so you included an intercept in your model. But what if you included beta naught, so you have an intercept in your model, and you include as the number of dummy variable equal the number of groups? This is a very common case of perfect multicollinearity. And that's a specification error, okay? And as I said last time, most softwares wouldn't actually estimate the model. It give you an error message, okay? So whether it is eViews or Stata or whatever software you use, I know you use eViews, but even with other softwares, it should be the same case. So with the Stata, actually, it does estimate the model, but it drops one of the variables. So actually, it does that on your behalf. But so it doesn't actually estimate all the dummies, or the coefficients for all dummies. Actually, it drops one of them. I give you some kind of warning message, and it tells you which dummy it drops. But with eViews, I think it definitely will give you an error message. It's not going to proceed. Okay. So, and as I said, this is a very clear or obvious specification error. So when you include an intercept and you include the number of dummies equal the number of groups. So if you have a gender variable and gender are two groups, male and female, and then you included two dummies and an intercept. In that case, with eViews, it gives you an error message. With a Stata, it's likely that it will drop one of the two dummies, and it will tell you, give you some sort of warning message which variable it dropped. So this is something very rare. So you're not going to encounter this very often. So because it's mainly a specification error. So for another example of perfect multicollinearity, for example, if you include income variable in your consumption function, so let's say consumption depends on income, and for whatever reason, because your data included two columns or two variables that represent income, one is measured, let's say, by pounds, and one is measured by pence and whatever, and then for whatever reason, by mistake, you included both. Okay, so both are actually the same variable. Okay, so in that case, again, so it will give you some error message. It's not going to estimate the model. This is actually a specification error. This is perfect multicollinearity. So we're not really worried too much about perfect multicollinearity, because we know this is mainly a specification error, and we will kind of receive an error message or a warning message from the software we use. So it's not really a big deal, because it's very easy to find out that you have a problem or you have an error. So the main issue here was actually imperfect multicollinearity, because in that case, your explanatory variables, your x's, are actually correlated, are highly correlated, and you're not going to receive any warning message from any software you're using. So actually it's going to estimate the model. You're going to have estimations. You're going to have coefficients that you actually can interpret, but this has some implication to your estimation. So as I said, so when we talk about perfect multicollinearity, you don't need to worry too much about it. But just as a quick example, if this is my model, y is a function or depend on x2, x3 till number of variables xk, and for example here, if x2 plus 3x3 equal 1, okay, this is perfect multicollinearity. Why? Because you can express one of these variables in terms of the other, and it's kind of linear relation. You see, this is linearly or collinear, so it's correlated linearly with x3. So x2 equal 1. So you just rearrange this, it will give you this one. So that means I can express x2 in terms of x1. So it depends on, it's a kind of linear relation between x2 and x3. And as I said, in this case, you have perfect multicollinearity. This is a very clear or very obvious example of a perfect multicollinearity issue, but the problem here, you cannot actually include both, and as I said, you're likely to receive a warning message in Stata and an error message in eViews. So it's not, as I said, it's not a big deal because you actually will be warned about it. The main issue here was actually imperfect multicollinearity. So the imperfect multicollinearity, following the same example, so we have a semi-regression model, but now x2 plus x3 plus 3x3 plus some sort of error equal 1. So in that case, so there's no perfect correlation between x2 and xy, but actually they still highly correlated. So the only difference here is that new error here that makes them not in not perfectly correlated, but they still highly correlated, and that's the case that we deal with most of the times. So most of the times you'll be dealing with imperfect multicollinearity rather than perfect multicollinearity. So that's why I'm saying this is the big deal. This is the problem, okay? Because perfect multicollinearity you'll be warned about, or you will receive an error message, or somehow you'll find out this is some sort of specification error. It's very easily to detect that. But with imperfect multicollinearity, it is the main issue here. So we're talking now, okay, so we assume that multicollinearity, or we assume that there's no perfect linear relationship between or among the x's. So we wanted to test for that, but just before we know how to find out whether we have multicollinearity or not, let's just ask the usual question or the normal question: what if there's imperfect multicollinearity? How this is going to affect our estimation? That is the main issue. Okay, what are the consequences or the implication to our estimation if we have multicollinearity? Okay, so Wash, well, OLS is still blue. So what do we mean by blue? Best linear unbiased estimator. Okay, so it's not going to affect OLS estimation. However, so even though if your OLS estimation is blue, okay, which is something we actually happy because it is blue. We want it to be blue, so it's kind of desirable properties of our estimator. However, you will have also you will have high R square, which again is something that we happy with, because that means our model explain much of the variation in our dependent variable, which is great. However, you most likely to have many insignificant or statistically insignificant coefficients, and this might not be necessarily the case. It could be just because of the multicollinearity that exists. Okay, so even you would expect statistically significant relationship, your model sounds okay or looks fine because you have a high R square value, But however, when you look at your individual coefficients, you find them statistically insignificant, which kind of is not what you expected, or is not what theory would suggest. So there must be something wrong in your specification or in your model. And in these cases, it's likely to be the case with multicollinearity. And also another sign to have this problem is that your regression coefficient will be very sensitive to small changes in your regression. So if, for example, if you estimated the model, if you re-estimated the model with a subsample, so you change slightly the sample, then you will find your result change significantly. Okay. So again, this is another sign. So what I'm talking about here are signs of the presence of the problem of multicollinearity. Okay. So whenever you have these signs, then you should doubt, you should have some suspicion that you actually have multicollinearity in your data, okay, or in your estimation. So in that case, if you have multicollinearity, so it's very difficult to isolate the impact of each variable separately, because the variables are actually related. They are correlated together with each other. So again, just to sum up the idea, just before moving on and trying to see how to test for multicollinearity, let's just again slow down, just go back to what we're trying to do, what we're trying to cover in this point. So we're trying to say, okay, we have assumption 6, we made a number of assumptions about our regression model. What we're talking about now is assumption 6, which says that there's no perfect linear relationship between your x's, or among your x's, or among your regressors, okay, or the variables on the right hand side. These are all the same thing. And we make this distinction between perfect multicollinearity and imperfect multicollinearity. So with perfect multicollinearity, we said it's very rare, so you're not going to find or to encounter this very often in a real situation, because it is likely to happen only by error or by mistake. So there is a specification error. And as I said, the most popular or common example here is the dummy variable trap, or when you actually by mistake, when you include the number of dummies, so you have an intercept and you include the number of dummies equal the number of groups. Okay, so we always said this is the rule of thumb here. So if you have a number of group G, then the number of dummies enter your model should be G minus 1. So you always drop one a group, and these group usually assigned 0. So you actually the value of 0. So that's actually your comparison group, or this is the group you compare with, or your reference group, your benchmark group. So this is mainly due to specification error. So you actually by mistake included the number of dummies equal the number of groups plus an intercept, and then as I said, this shouldn't be a very big deal, because, well, it is a big deal actually. So my point is that it's easy to find out about. So it's easy to see, okay? Because Stata will give you a warning message, eViews will give you an error message. So actually, it's very clearly that there is a problem here. Okay, so it's very easy to find out about the problem. So it is a big deal. I don't want you to misunderstand what I said. So my point, I'm not worried too much about this, because you will be warned about it. So your software will tell you there's a problem here. Okay, so that's fine. But with imperfect multicollinearity, when you're actually your x's or your regressors or your independent variables are highly correlated, the software is not going to actually warn you. Okay, it's going to give you results. Okay, and that is the problem, because if you try just to explain your results, and you may conclude that there's no significant relationship between two variables, well, actually theory suggests there should be. Your data also, if you have the correct model, you should find these coefficients statistically significant. So you're actually concluding something that, again, is what you would expect, and again, is what the theory suggests. It's just because there's some collinearity. So there are two or more variables on your right and the right-hand side are actually correlated. Okay, and that is the main issue here. So, and that's I was saying, I would worry about this more because of that reason, because you could just proceed to estimate a model that actually is not correct. Okay, and the problem here comes from the fact that you're not warned about this. The software doesn't warn you about this. You get results. You try to interpret the result and build on those results. So, just looking for a very very simple example, just snapshot from one of the textbooks. So what we have here, we have the dependent variable expenditure. So let's say there's a researcher who wished to estimate a model that explain how much, like, households or individuals or whatever your units are spend on expenditures. So you have data for, so your dependent variable is expenditure. Your independent variables are income and wealth. Okay, so what we have here, so theoretically speaking, you would expect your income affect your expenditures. Okay, and also if you are wealthier again, or wealthy, then you expect to, again, that would affect your expenditure. But looking at the estimated coefficient, or looking at R squared first, so R squared is very high. We have 0.96. It's very high R squared, so that means these two variables, or my model, should explain much of the variation of expenditures. Okay. However, when you look at the individual coefficients, you find that these individual coefficients are statistically insignificant. So if you look at the t values, which underneath these coefficients, these are very small values. So you will fail to reject the null hypothesis that these coefficients equal 0. So these coefficients are not statistically significant, or are not statistically different from 0. So my conclusion in this case, that wealth and income do not determine your expenditure, and that's a mistake. Okay, so, well, theory suggests that, even like a very simple, like any intuition would suggest that you would expect that income affect expenditures, okay, wealth affect expenditures. But then when we run the model, when we estimated the model, we found that the coefficients are not significant. Where is the problem here? Yeah, I hear something coming from the side. What's the problem here? Come on, income and wealth are correlated. So that's very, very obvious. Okay, so income and wealth, these two variables are correlated. Okay, so if I drop one of them and I estimated the model again, so we'll just go to the second line, or the second estimation. So you still have expenditure on the left hand side, and you have only income on the right hand side. Okay, and that turns out to be statistically significant. Look at the t value here, the t statistic here, sorry, the t statistic is 14.2. So it's jumped from 1.1 to 14.2432. So that's definitely statistically significant. It's actually very highly statistically significant. Okay, so this is the t statistic. Okay, so it's very high value for the t statistic. Obviously, you should go to the t table and get the t critical and compare this with. But given that the t statistic is really high, 14 is very high, then I don't really need to go to and look in the table, because it's really high. 14 is very high value for the t statistic. So my conclusion here would be much different from what I concluded a few minutes ago, when I thought that income is not one of the determinants of expenditures because of multicollinearity that exists, because of this linear relationship or correlation between income and wealth. So my first conclusion was wrong, just because of multicollinearity. Okay, so when I run a regression only including income without wealth, then I find out that income actually is statistically significant. And if you look at the third estimation with using only wealth on the right hand side, then you'll find that wealth also is statistically significant. So also it determines expenditures, and you look at the T statistic here, jump to 13.9. Okay, so it's very highly significant. Okay, it's not just significant; it's actually highly significant. So, and that's in line with what we would expect, because wealth affects expenditures, income affects expenditure. Okay, it will affect how much you spend, and having both variables that are collinear, or they are correlated in the same model in the first specification, that causes multicollinearity. And as I said, one of the signs of having multicollinearity is that you have a high R square, but then a statistically insignificant coefficient. And that's exactly the first estimation. That's what happened in the first estimation. So just out of curiosity, you could say, okay, what if I run a regression between wealth and income, see if they are actually correlated or not. And that's the last one. So wealth and income. So wealth is the dependent variable. Income is your independent variable. And when you look at the T statistic, it's 62. So again, very highly statistically significant. That means they are very highly correlated, these two variables. Okay? So it would be a mistake. It would be really incorrectly adding these together into the same model like the first equation or the first estimation. That will lead to a wrong conclusion. Okay? Is that clear? Okay. So how to test? So far we talked about signs. So what we have here, there are different things that you could do actually. These are not a formal statistical test, but things that you can do to figure out whether you have multicollinearity or not. Okay? So the first sign, as I said, or the first symptom you could have is the high R square, but very few significant T ratios or the T statistic. You could also have the correlation matrix. So you could produce the correlation matrix between your variables, your x's, and then see how much they are correlated. Okay? So just looking at the correlation coefficient between these, each pair of your variables. You could also run an auxiliary regression. This is called auxiliary regression. The wealth. What I did here, I just picked one of the regressors, and I run a regression against the other regressors in the model, which was income. So that's called the auxiliary regression. So if you look at this and you find if a statistic that's highly significant or significant, that means there's correlation between your x's. There's also another thing that you could do. You could calculate what we call the high variance inflation factor, or the variance inflation factor. So if it is high, okay, that means you have again multicollinearity. And what that does actually, it is the variance inflation factor for xj, for one of the x's, would equal 1 over 1 minus r squared for that x. Okay, and in that sense, you actually run a regression of that x, let's say xj, against an intercept and the other regressors in the model, so the other x's, and then you obtain r square, and this will calculate this 1 over 1 minus r squared, and that will give you what's called variance inflation factor. So there's a kind of, there's no really like a universal agreement on how much that should be. Okay, some people say if your variance inflation factor is greater than 10, so that means definitely this variable is causing a problem or is causing multicollinearity. Okay, but some others will look at 7. Some others, like let's say between 5 and 10, or anything above 5 will cause a problem. So anything that we would imagine or we would consider high, then that means there is a problem caused by this, or the problem of multicollinearity that's caused by this variable. But again, as I said, there's no really an agreement on what value you should be looking at. Most people will look at any value above 10. Some people go actually low than that. They go to 7 and even anything above 5. But it's not a big deal again. So it's something you could do with other stuff. So you could, I would personally look at the correlation matrix It's very simple, okay? The idea here is that I want to know whether these x's are correlated or not, so just calculate the correlation, okay? And it's something very simple you can do very easily in eViews or any other software. Also, I'll show you how to calculate the variance inflation factor now in eViews, so it's very straightforward. But my point is just because it's not really clear, there's no clear-cut answer. Where's the threshold, where's that value that after which I will say there is perfect multicollinearity because it's a high variance inflation factor, then you probably need to do something more, not just looking at the variance inflation factor. You could also do some auxiliary regression, the same way I did wealth in the previous example, and then look at the if test or if statistics, see whether it is statistically significant or not. Okay. Let's just quickly just look at an example. But before we do that, do you have any questions? Is the idea of multicollinearity clear? Okay, it's very simple. If there's correlation between your x's or your x's are highly correlated, then there's a problem. There's multicollinearity. Okay, and this multicollinearity, one of the main issues here. So as we said, well, your OLS estimator might still blue, which is great. However, you might actually conclude something that's not correct. Okay, just always remember that example of expenditure when you run a regression on expenditure on wealth and income. So anyone, if you ask anyone that who never studied economics, do you expect income to affect your spending? You'll say definitely yes. Do you expect your wealth to affect your, or to influence or to determine your spending? Well, definitely yes. Okay, but then when you run a regression, you say, just tell that person that who never studied economics, well, no, you don't really understand anything. I'm the specialist here. I run a regression, and I came up with a conclusion that they don't. It's actually very foolish because actually they do. But the only problem here, or the main problem here, that these two variables are correlated. And when you run a regression with these two variables on the right-hand side, they cause multicollinearity. And in that case, you will have high R square. But then when you look at the individual coefficient, you find that they are not statistically significant. So you need to be aware of this problem. Okay. So as I said, how to find out? Again, so the main symptom here, we have high R square, but individually statistically insignificant coefficient. And also we could do correlation between, you could just calculate the correlation between the x's, and then when you have high correlation between two variables, then you should recognize where, or should understand where the problem comes from. Or you could do the, as I said, you could do the variance inflation factor. And the way we calculate the variance inflation factor, if you want to calculate it for 1x or xj, so that means you run a regression, xj is your dependent variable, and then on the right hand side you include an intercept and the rest of the regressors in your model, or the rest of the x's in your model, and then you obtain R square from that regression, and then you calculate this is 1 over 1 minus R square. And again, if it is more than 10, some people think of 6 or 7 or anything above 5, then that means that x is causing, or there's some sort of multicollinearity because of that. So in the example we'll cover now, we have data about married women's hours of work, and this data come from this paper. And what we're trying to do, we're trying to assess the impact of several socioeconomic variables on how many hours married women would work, or a married woman would work. So we have cross-sectional data on 753 married women in 1975. And among those, we found that only 325 women, actually, these women didn't work, so the rest work. So what we're trying to do here, we're trying to estimate a model where on the left-hand side we have the number of hours married women work, and on the right-hand side we have a large number of regressors, a large number of variables that we think they are important to explain how many hours a married woman would work. And these include age, education measured as years of schooling, experience, family income, father education, husband's age, husband's years of education, of schooling, so husband's education, hours worked by husband, and husband's hourly wage, the number of kids between 6 and 18, the number of kids under 6, and wage, mother education, marginal tax rate, and unemployment rate. So we have a really large number of variables in this data that we think might be important when we explain the number of hours a married woman would work. So usually before you estimate the model, before you run t-views and include your data or import your data and e-views, you should ask yourself first, what do I expect here? In terms of, at least in terms of the sign, how these variables, how these large number of variables here, how each one of these variables should affect, or are expected to affect or to influence that dependent variable, the number of hours of work for a married woman. So some of course, like education, maybe a more educated woman will work more hours. Maybe if a woman with more experience would work more. So we might expect like positive sign for these coefficients, for these I'm happy to answer any questions you have, by the way, so you don't need to ask the person next to you. So on. So my point here is that always think of your expectation to the sign of your estimated coefficient, and think of what theory tell us about that. Okay, so if we expect if the let's say wages is high, or let's say or higher wage, would that mean that married women would work more or less? Again, look what theory suggests about that, and so on. So before you run the regression, then just try to think about the common sense, the intuition, the theory, how your variables interact with each other. So this is the estimation. I don't think it's very clear, so I'm just kind of zooming in. Okay, so you don't have to worry about the slide that I just skipped. I'm just zooming in here in that table. This is the estimation in e-views, and you'll see, if you notice, the dependent variable is the number of hours a married woman work. And notice here that I actually restricted my sample to those with hours that more than 0, that greater than 0. So if you look at 1, 2, 3, 4th line, you'll see sample 1 to 753. This is the total number of observation. But then I put some condition here to restrict the sample, which is if hours are greater than 0. Okay, so that means I actually have 428 rather than 753. Why? Because the rest are not working, and I want to model how these variables determine the number of hours a married woman would work. So again, I'm actually concerned. I want to study those who actually work. So those who don't work, those who have 0 hours, I exclude them from my sample. So what we see here is only those married women who are working actually. Okay, so and then we estimate the coefficient. So if you zoom in this table and you look at the estimated coefficient, so for example, you would imagine that age, education, experience, these variables should be statistically significant, but they are not. And at the same time, when you look at R square is fairly high because this is cross-section data, so it's not too bad really, 0.33. So my point here is that when you look at these estimated coefficient, which economic theory suggests that these should be important in determining the number of hours a married woman would work, However, when we look at the estimated coefficients, when we look at the p-values here, uh, you see the p-values in most cases actually is not significant. So it's large p-values. So it's more than 5%. It's more even than 10%. So with the case of age, education, the father education, the husband wage, the husband age, and etc. I think even the husband hours, etc. So most of these coefficients, unemployment rate, for example, again, it's not significant. So this coefficient, many of them we would expect to be significant, but they are not. Okay, and again, why? Because some of these variables are actually correlated. Okay, and that is the main issue here. Okay, so what we need to do then, when we have correlation, when we suspect that we have multicollinearity, what should we do? So another way, actually, one more thing we could do, as I said when we talked about how to detect for multicollinearity, we said, okay, we could have this as a sign when we have high R squared but few significant coefficient, but also we can produce or calculate the variance inflation factor. So I just want to show you quickly how we can get this. But remember, as I said, most people look at variance inflation factor values that are higher than 10, but some people would consider anything above 7 or 6 still high. But in views, you could actually produce that easily, so you don't really have to do this for each variable, like to calculate it by hand, 1 over 1 minus R squared, but you should really understand what that, how that was calculated. But in views, it's very straightforward. When after your estimation, you go to view coefficient diagnostics, and then you'll see that there's variance inflation factor there. So once you click on that, that will give you a table of variance inflation factor. And as I said, so you could look at this last column here, and as I said, maybe 7 here, 7.2, that's high. Maybe, as I said, maybe these coefficient with these variable with 5 plus maybe could be considered high. So the reason here is that I'm not very clear about which value really or how much would be high. As I said, there's no really much agreement on that, but most people would think of 10 plus, like anything above 10, so definitely, so everyone would say this is high, but some people argue that actually could be even lower than that, but still causing issues. And I think something which I didn't consider here in the lecture notes, but you could actually do, which is the correlation matrix. So just do the correlation matrix between your x's or your regressors and decide which variable might be highly correlated with which variable, and then what to do. So now we know what multicollinearity is. We know that the estimation we have, there's an issue of multicollinearity here. We are very suspicious about this estimation. We can't proceed to interpret this estimation because we know that we have most of these coefficients are not statistically significant at the time that we expect they should be statistically significant, and we know that these must be correlated, or some of these variables must be correlated. So then what should I do? Okay, mainly you drop the variable that you think is causing the problem. Do you remember what we did with expenditure? When we estimated that model of expenditure based on income and wealth, we said, okay, we can't actually include both variables in the same model. So you either study how income affect wealth, how income affect or determine expenditures, or how wealth determine expenditures. Including both variables in the model wasn't correct because these two are highly correlated. So what we would do here, you could drop or exclude the variable that you think is really highly correlated with other variables and is causing the main issue or the main problem of multicollinearity. But then you just have to be very cautious when you do that, because you might fall in the problem of omitted variable bias, and this is something we will discuss next time. But very briefly, when you have an important variable and you don't include in the model, then the effect of that variable goes into, where does it go? So if I drop an important variable from my model, the effect of this variable will be captured by the error. That's why we have the error term. Do you remember? That's why we do have an error term. Okay, so the effect of this variable will go into the error term, and that will cause a bias, or you will cause that OLS estimator will be biased, so they're not going to be blue. Remember, best linear and bias. Actually, it will make it biased because there's an important variable that we excluded, and its effect went to, or is captured by the error term. So this is something we will discuss with the specification errors next time. So we'll talk more detail about specification errors next time, but just in case you're wondering what omitted variable bias mean. So the solution here, we dropped the variable that we think is causing the issue, or is really highly correlated with other regressors, but then just to be a little bit cautious in that case. Another way to deal with that, if you have really large number of variables, and these variables are highly correlated, you could do something called principal component analysis, which we're not covering this in this module. Okay, so that will reduce actually the number of variables. That would produce a different type of variables that actually should eliminate this sort of correlation, because these should be independent. So it shouldn't be correlated, these variables. But as I said, this is not something we will cover in this model. So in our case here, so when I drop some of the variables, this estimation or the estimated coefficient become most of them. So for example, age and education were not statistically significant. Now it turns out that they are actually significant. Okay, and the same case with the husband hours, the family income. So all these coefficients became significant. Remember, all these coefficients were not significant in my first attempt. And again, when I dropped some of the variables that I thought might be causing the issue, so this is kind of refined or revised specification, because I knew that there's multicollinearity, and turns out here that actually, yes, these variables are important in determining the number of hours a married woman would work. Okay, so it's just a matter of understanding your variables, how they are correlated with each other. Is multicollinearity clear? Any questions? Okay, I heard so many questions, people talking with each other, so I'm sure you have questions. Any questions? No questions? Okay, let's have 8 minutes break. Okay, I'll see you in 8 minutes. We'll come back and talk about it. Okay, guys, let's start. Okay, so in the first half of the lecture, we covered multicollinearity. We explained what multicollinearity means. We explained that this is assumption 6. We made a number of assumptions about our regression, and one of which was assumption 6, which means which states that there's no perfect linear relationship among the regressors. We saw how this affects our estimation, how to detect for it. There are many symptoms. There are ways to find out whether you have multicollinearity or not, and then what to do. What we said so far is just maybe you should drop the variable that you think is causing the issue, and then just be cautious about not to fall in the omitted variable bias issue. And then we said there's another way to deal with it, which we wouldn't cover in this model, which is the principal component analysis. Especially if you have large number of regressors that are highly correlated, then you might use this to produce actually a number of variables, or a number of they call it principles, or principal components, the number of components that are not actually correlated at all. So, but they still explain most of the variance in your data. And this is something we're not going to cover. So, but the example we show how most of the variables we had, we estimate the model, we had a fairly high R square, given that this is cross-section data, but in the same time we found that the estimated coefficient were not, most of them, or the majority actually, were not statistically significant, which was against the common sense or the intuition. and also theory as well. So we thought, okay, this doesn't make sense. There must be something went wrong in our estimation, and that was multicollinearity. When we drop some of the factors or some of the variables, then the estimation tend to be mostly statistically significant as we expect. So in that case, that means if you suspect that there's one variable causing the problem or one or two variables causing the problem, just maybe you need to drop one of these two variables. Then we'll move on now to talk about heteroskedasticity. As I said in the beginning, we're going to cover two assumptions. The first one was A6, or assumption 6, which we already covered now in the first half of the lecture. The second half of the lecture, we want to talk about heteroskedasticity, and that was assumption 4. So in assumption 4, we assume that the errors have, or the error term has a constant variance. A constant variance, so it is not usually the case. So again, we would love to have these assumptions true, so then we can be happy with our O list, that is, it is blue, best linear unbiased estimator. But then when these assumptions, one or more of these assumptions are not true, then this might not be the case. So in this case now, or in this assumption, the assumption number 4, the variance of the error term should be constant, but this is not likely to be the case, especially if we have cross-section data. So usually in cross-section data, it's very difficult to have to estimate a model where your errors are actually homoskedastic or has constant variance. Okay, so and sometimes you have, maybe if you have outliers, or if you have, so outliers means like extreme values in your data, or if you have incorrect functional form, etc. So different reasons why you might have a variance, so an error that doesn't have a constant variance. Sorry. So for example, if we have y here represent the savings, and x is your income, represents your income, then as income increases, savings on average also increases. So if the assumptions that we made, the A4, the assumption 4, if that assumption which we made about the error variance, if it was true, then that means the variance of savings remain the same at all levels of income. So if you look at this, it's kind of what you see now. So the way they spread around that regression line, they seem to be the same. Okay, in that case, we said, okay, the variance of ui, or the error term for I, equal the expected value of the ui squared given xi, that should equal sigma squared. So sigma squared here is just by conventional. So this is what this is how we denote the variance. So it's sigma squared, and given that is sigma squared is a constant, so that means it means constant variance, and it's called homoskedasticity, or homoskedastic error, means equal spread. So it's spread equally around that line. If you can see 1, 2, 3, so these are 3 points. You see that how they spread nicely around. They are equally spread around the around this regression line between income and saving. If you compare this, I mean, this is the ideal case. This is what we would love to have, but this is not reality. Okay, so this is not what we have in reality. So this is what we ideally would like to have in an error term, to be spread that way equally, or homoskedastic errors that has equal variance. However, in reality, you're most likely to find something like this. So these are not actually, they don't have the same spread. In that case, we call it, that's why it's called heteroskedasticity, or heteroskedastic, so unequal spread. So just think of it as that way. So in that case, if you want to represent that, you'll see the variance of ui, okay, it's expected value of your error squared given x equal sigma I squared. So now we have this subscript just to denote that actually the variance is different depending on which observation or which individual you're looking at. So here, when you look at these, how the way they spread around this regression line, so they're not actually they're not the same variance, and that means these are non-constant variance. Non-constant variance, and that is the problem of heteroskedasticity. Okay, so homoskedastic error, this is the equally spread error. These are errors. That's what we like to have. Okay, this is our assumption 4, but this is not reality. Okay, what we have in most cases when you deal with cross-section data, so I always tell my students, if you have cross-section data, so by default assume that you have heteroskedasticity. This doesn't mean that you don't need to test for it. You should test for it. Okay, you should make some tests, or you should do some tests, or should make some effort to really find out whether you have heteroskedasticity or not. You need to prove that you have it. But anyway, my point is that in general, because of the nature of the type of the data you're dealing with, the cross-section data, then usually should expect that you have. So it's more common with cross-section data compared to time series data. But in all cases, you should actually do some tests to find out. So another example here is error learning model. So this was like a model of typing errors and hours of typing practice. Again, so you see, as you practice more, your errors, you become more accurate, and then the variance here actually is getting smaller. And again, so that means this model has an error that the variance is not, its variance is not actually constant, or change actually the same. Here, this is another example when we have outlier. Outlier means, as I said, kind of extreme value. So if you look at Chile here, again, it's just at the far right end there at the top. That means it's kind of, you see most of the other data points are kind of clustered or somewhere in this the left side, but then Chile is just very, very obvious that this is like an extreme value. And again, heteroskedasticity or unequal spread variance could be caused because of this, can happen because of these things. Okay, so this is just another example of. Okay, so now if we really understand what heteroskedasticity means, so heteroskedastic errors means that what we assume is homoskedastic errors. We assume that the error term, the variance of the error term is constant, but if you have the variance is not constant, that means you have heteroskedasticity or heteroskedastic errors, and that's the problem. Why is it a problem? Because it has some implication to our OLS estimator. Because if you remember from the first time we met together, we said when your assumptions are valid, so A1 to A7, that means your OLS estimator is blue. But now, if one of them, like this, one of the assumptions was assumption 4, if your errors are heteroskedastic, that means your coefficient or your estimations is no longer blue. Why? It is still is going to be unbiased, but it's not going to be efficient. Okay, it's not going to be the best. Okay, it's going to be less efficient. So that means one important, which is B here, the best, is no longer the best. It's no longer with, you remember when we said unbiased, we mean the expected value of your estimator equal the true parameter. That's unbiased. But best means that if you have a number of estimators, then the one that has the minimum variance will be the best. Now, given that our errors are heteroskedastic or has unequal or non-constant, that means the OLS estimator is not the best, is not efficient. It's less efficient, so it's not the best. Okay, so it affects the efficiency of your estimation or of your estimator, and that affects also the statistical inference, which depend on the estimated t values, and these become less reliable. So we could actually, if, as we will see at the end, if we know the structure of the variance, why the variance is not constant, we can actually transform this to become constant. That could be done by using the weighted least squares. So not O list, we're actually using something called weighted least squares. We will come back to this point at the end. But for now, let's just now agree that, okay, what heteroskedasticity is, what does it mean, and then what are the implications of having, or what the reasons we would have heteroskedastic errors, and then what are the implications. So our assumption, the error variance is constant. The problem when it is not constant. So if it was constant, then that means we have homoskedastic errors. Okay, equal spread errors, or the variance is constant. If it is not, that means we have heteroskedasticity. That is the problem. Okay, so heteroskedastic error is the problem. Homoskedastic error is not the problem. That's our assumption. That's what we would like to have. So if you have heteroskedasticity, what is the problem? Okay, as I said, it has some implication to your estimation, your OLS estimator. So OLS estimator is still unbiased. So unbiased means the expected value of your estimator equal the true parameter. However, it's not going to be the best. It's going to be less efficient. So that means it's not blue. Okay, and also it has some implication to your inference or your t values. So they become you can't rely on them, so they become less reliable, and you could actually make this blue if you can estimate this through the weighted least squares. Why would this happen? Why would heteroskedasticity happen? As I said, there are so many reasons, but what I would imagine is, or the case where I actually should suspect this heteroskedasticity to happen is when I have it's more common with cross-section data. So whenever you have cross-section data, you need really to worry about heteroskedasticity. Okay, so you need to. I mean, this doesn't mean that you shouldn't test, and you should say, "Oh, okay." Hani said that if you have cross-section data, then you have heteroskedasticity. So I'm going to just move on with that. I assume it is there. No, you need to test for it. You need to plot your data. You need to see your data, and you need to see the variance, and then you need to decide whether you have heteroskedasticity or not. And then that might help also in how you can deal with heteroskedasticity. But so far, what we know is what does it mean? What are the causes? And mean why it happened, and then the implication to OLS estimation. So with OLS estimator, we're still blue. It's still unbiased, but it's not efficient or less efficient. Okay. How to test for heteroskedasticity? One way you could plot your data. Okay, so you can graph histogram of your squared residuals, or you can maybe graph your residuals against predicted y. So how can you obtain the residuals? You need to estimate the model first. You estimate the model using OLS, and then you obtain the residuals, and I'll show you how to do that in eViews in a few seconds, a few moments. Okay, so these are like different ways how to actually informally, so you're not doing a formal test because you're just looking at the plot, but you actually could do some tests as well. So there are several tests, and they are very similar in many aspects. But what we're going to cover today is only two tests. We're going to see examples of two tests: the Brush-Begin test and the White test. Okay. So there are other tests, as you see. There are different tests, but we're not going to talk about these today. So we're going to explain these two tests. What is the null hypothesis? How to calculate the test statistic, etc. So just remember. So how to test or how to detect for heteroskedasticity. I hope now you know what heteroskedasticity means. Can you say heteroskedasticity? Can you say it? Is it easy to say? Well, it took me time to learn it. Okay, so it will take you some time to get it right. Heteroskedasticity. You see, I've been saying heteroskedasticity many times, but I didn't make a mistake so far. So hopefully, sometimes I find it difficult to say. Heteroskedasticity. You can try it on your own when you go home. Just to stand in front of the mirror and keep saying heteroskedasticity. You feel like that's foolish, yeah? So anyway, so well, it's not an English word, so You just live with it. It's called heteroskedasticity, okay? So you practice at home. And also, what I actually struggle with is actually spelling it right from the first time. So, I mean, you're not going to see it in, and if you have like a dictionary that corrects your typing in Word, I don't think this word will be in your dictionary. So you have to include it. But just make sure that you type it right first before you include it, so you avoid including the wrong spelling. Anyway, so let's just go back to the point. So we know what heteroskedasticity is. We know that the causes of heteroskedasticity. We know the implication of, or the consequences of heteroskedasticity. Okay. Now we need to know how to test for heteroskedasticity. As I said, the informal ways to do that, you just plot your data, or you plot your residuals, mainly because we are concerned about the variance of your residuals, or sorry, the variance of your error term, but you'll never see the error term. Remember, I think I said that many times before. You don't know the error term. What we have actually is the residuals, and the residuals, we usually use the residual as a proxy for the error term that we don't see. So you don't see beta, you always see beta hat. You estimate beta hat. Okay, that's based on a sample. Okay, so the same intuition applies to the error term. So you don't know the error term. You're not going to see the error term. Okay, we wish we could, but you're not going to see it. But what you have actually is the residuals. So once you estimate your equation based on all this, and then you obtain the residuals, that's a fair proxy of your errors. But anyway, so what we're studying here is the residual square. So what you do, you plot this residual square, and then you look at if there's like a clear pattern, then you would suspect there's actually heteroskedasticity. If not, then there's no heteroskedasticity. So, but all these, as I said, these are just graphs, and these are like, there's not like informal, these are not formal tests or statistical tests for heteroskedasticity. The formal tests are these examples: Bruch-Pagan test, White test, and that's what we're going to talk about in a moment. So these are just like examples of ways when I plot the residual square against y hat, and like if you see like kind of relationship, like it seems like there's like a very clear pattern that this means that there's a relationship between your residual square and the predicted value of y or y hat, and that means you have heteroskedasticity. I think the easiest way to do it is to actually go to an example. The easiest way to understand it. So let's say we have data to model abortion rates. This data is available. It's 5.1, table 5.1. And these data come from 50 US states, along with other characteristics, such as religion, price, laws, funds, income, etc. So we want to regress abortion on characteristics on the other variables that we think will explain abortion rate, how these are in different states. So is this cross-sectional time series data or panel data? What is this data now, the data set we have? Is it cross-section, time series, or panel data? Cross-section, yes. So you have data for a number of units. We don't have dates here. We don't have variation over time, so we don't have t. It's only one point at time, but there's a number of units. That's cross-section. So since you have cross-section data, you should suspect you have heteroskedasticity, okay, or non-constant variance for your errors. Okay, so let's say now we've done a good job. We actually estimated the model, okay, and as you see, we have 50 observations in this data set. Abortion rate is our dependent variable, and then the other independent variable there. We estimated the model, so we could just go ahead and estimate, interpret this coefficient. But what is the problem? The problem is we need to test for heteroskedasticity. Why? Because if the errors are heteroskedastic, or they don't have a constant, or their variance is not constant, how this will affect our estimation? This is all this estimation, remember? Okay, exactly. So what is going to happen? So our estimation will still unbiased, which is great. There's something we'll be happy with, but it's not going to be blue. It's not going to be the best. It's going to be less efficient. So that means also I cannot rely on these t statistics and obviously the p-value as well. Okay, so mainly we need to test whether these are. So one way to test that is actually to plot the graph and to get the residual from this data and to plot it against the y hat. So to do that, what I did here actually, I went to this tab on the top after the estimation. I went to forecast, and I think I get the predicted value, which is the apportion. I call it apportion F. I just give it a name, this whatever name you want, and then I plot this variable against the residual square. Okay, so again, let me just go back to this point. So what I said here is you could graph the squared residuals. Okay, so in eViews, you know there's an object in eViews always for residual. Do you know what is it called? So when you use eViews, have you used eViews before? Yeah. Okay, good. So there's always reset, you see? That's for residual. So whenever you estimate a model, whenever you run a regression, so automatically your residuals are saved in your reset object. Okay? So if you have, anyone has his or her laptop now and you go in eViews and you, whatever regression you run, you will all see this object reset. So that reset is actually an object that always keep your residuals from the last regression you run. Okay, so that's something we have. Then the squared residual, you can just you need to square that one, so you can just get the square term of that one. So again, it's predicted y. So what I was trying to get from eViews is the predicted y hat. Okay, so the way to get y hat, so I wanted to get this one to plot against the squared residual. So what I did here is I estimated the model. Okay, so once I estimated the model, resid already now contain the residuals, so I can get the square term from that. So that's very straightforward. However, I still need the predicted y or y hat, and the way to get this is just go to that tab after your estimation forecast, and then when you click there, it will take you to this whatever you call this is the forecast, and then you can just give it a name, and that will create a new variable which will have the forecast name. So you give it whatever name you want, and that then you could actually, now you have two variables that you could actually plot together. So this is what I did now. And what we can see from here, as I said before, if you can see like a pattern or a relationship between both, that seems it's a sign that you have heteroskedastic errors. And that's exactly what we have here. So okay, you see that regression line which I did, or that red line is a regression line between both. So when you plot these, it seems there's like a pattern here that we can see. So that means we should suspect that it's a sign that we have heteroskedastic errors, or errors that has a non-constant variance. So this is an informal way of detecting heteroskedasticity. So what else can we do? We could actually do the Bruch-Pagan test. As I said, we will cover two Bruch-Pagan tests and white test. So how does the test work? So with Bruch-Pagan Goodfried test, what you need to do is to estimate the model, which you already did using OLS, and then you obtain the residuals. And then what it actually does, it regresses squared residuals on the regressors in your model. So let's say you have k regressors. K, that could be any number of regressors. So you regress the squared residuals on that number of regressors, and then your null hypothesis is homoskedastic errors, something we like. Okay, if you reject that, then that means you have heteroskedasticity. So you have the problem of heteroskedasticity. Okay. If you fail to reject, so that means it's great. We don't have heteroskedasticity. Our errors are homoskedastic or do have actually constant variance, which is the desirable property that we would like to have in order to have a blue estimation, or in order to have OLS blue. Anyway, so how to make a decision? So what we have here, we have a regression where we regress the squared residuals in the left-hand side on a number of regressors. Then you can actually use F statistic from that regression, and this with k minus 1 and n minus k, this is how to get the critical value from the table. And then if you compare these two, okay, then if the computed or the F statistic greater than the critical value, then what should you do? It's like any F test. You did F test before, didn't you? You did T test at least. Okay. So with a T test, what do you do? How do you make a decision? Reject or not reject the null hypothesis? So if your statistic greater than the critical value, then you reject the null hypothesis. Okay? It's the same rule with t-test, which you did. It's for the f-test, which you did before. And this is, again, it's the same if-test. Okay? So the idea here is you have a formula or a way to calculate your test statistic. All what you need to do is to find the critical value. And since this is an F statistic, so it follows F distribution. So you go to the F table. So you go to so F table with these to get the critical value from the table with these two k minus 1 and n minus k. However, you still can look at the p-value because your software eViews will actually produce the p-value for this F statistic. We can make a decision based on that. That's fine. Okay. So the idea here is that the same way we did with T statistic. So what we did, we could look at the critical value, but we've been actually relying on the p-value. So because they should give you the same conclusion anyway. Okay. So what we're going to do here, okay, we run this regression, and then we obtain the squared residuals. You run the squared residuals on regressors. You know that your null hypothesis is homoskedastic error. You get F statistic. Again, it's F critical. If F statistic is, which I call here computed F. So if your F statistic greater than your critical value, then it is significant, means that you reject the null hypothesis. If you reject the null hypothesis, meaning that you have actually heteroskedastic errors. So, oops, sorry, I just need to move forward. Yeah, so this is how you do it in eViews. You see, that's the fun now, because you don't need to worry about what I said, but you still need to understand what it does, because in eViews you can just you can do a few clicks, you get actually the test done for you, but you still need to understand how the tests work. So from view, you see, after you estimate, so after you finish, you do your estimation, you go to view, and view there's residual diagnostics, and then you go to heteroskedasticity tests. Okay, we agree you're going to practice saying heteroskedasticity at home. So, but I'm sure you will recognize it. So it is there. So it's very easy to. It's the most weird way word you will see in there. So it's very it's very easy to find, not very difficult. Anyway, so once you do that, so it gives you a list of the tests that you can do. Okay, and as I said, we going to cover the first one and white. So you got this one, Brush, Bacon, Good Friday test, and white test. So you can choose them for the same menu. So in this case, because since we're talking about Brush, Bacon test now, so we'll choose the first one, and see on the right side what does it call? What does it say? It say the dependent variable is residual square. Okay, so you know that this is your dependent variable, and then your regressors. These are all the regressors I had in my model. Okay, so I just added them all. Okay, and then once you press OK, that will give you the results. Oops, sorry. Okay. I assume you can see that, but I'll tell you what is the p-value. It's very small, I know. So if you look at the first line, you'll see on the left F is statistic. Okay, I'll read it for you. So it's 2.8. Okay, so if I want to know whether this is statistically significant or not, so I can reject or not reject the null hypothesis, you could actually rely on the probability, which is the p-value, which is called probability F, prob.f, which is again the first line at the top. You'll see that's 0.0167, which means it's smaller than 5%. Okay, so that means you should reject. Yes. So once you reject, what is the null hypothesis? Your errors are cute. Your errors are homoskedastic. They have what you want. Yeah. So when you reject that, and they are not. Okay. That means they are heteroskedastic. They don't have constant variance. Okay. So we reject the null hypothesis. The null hypothesis is homoskedastic errors. Your errors have constant variance. So you really, for any statistical test, you really need to ask yourself, what is the null hypothesis? Okay? Otherwise, you cannot really make the right conclusion. Okay? You need to understand what is the null hypothesis. In this case, with Bush-Biggen test and in Y test as well, is the same null hypothesis. Okay? So your null hypothesis is errors are homoskedastic, or the variance of the error is constant. You have constant variance. Okay, so if your statistic, or if your tested statistic, which is F here, is statistically significant, mean that you reject the null hypothesis. Rejecting the null hypothesis in Bush-Biggen test and the Simon-White test mean that yes, you have heteroskedastic errors. Okay. So yeah, so it's very easy. What I want to say is very easy really to do the test, but you need to understand the test. But then when you look at the lower part of this, or the second part of this table, you will see the equation, the test equation. So in your test equation, you see the dependent variable is residual square. So it actually tells you how it implemented the test, and you'll see the regressors which we included there. Okay. So my point here, okay, you can make an easy decision, or you can run or implement the test very easily in eViews, but I want you to understand what the test does. Okay, so it's very important not just to click, not to be able to do a few clicks and get the results, and also interpret the results. To interpret the results, you really need to understand what the test does. Okay, in this case, as I said, this is what the test does. So you run the regression, you obtain the residuals, you get the residual square, you run this a regression of the residual square on the regressors, and then use the F statistic. And in this case, as I said, you don't really have to go to the table, but if you have to, then if the F statistic, the computed one, is greater than the critical one, then you reject the null hypothesis, which means you have heteroskedasticity. Okay. In our case, we didn't need to go to the if table, because we actually have the p-value which we can use to make a decision. So in our case here, p-value is very small. It's actually 0.016, which means it's smaller than 5%. That means we reject the null hypothesis. And again, the conclusion is heteroskedasticity. We have, or the presence of the problem, or the presence of heteroskedasticity, which means our variance, or our error has a non-constant variance. So the variance is not constant. Okay, so this is one way. Another way is to do Y test. Okay, so any question? Okay, so what we have here is very similar to what we did. Again, you need to regress the squared residuals on regressors, but it does more than that. So not just the regressors, it actually adds the square terms of these regressors. So if you have squared residuals on X, that's what Bush-Biggen test does. Just run this regression, the squared residuals on X's, all your X's. But with this, with Y test, actually does more. It does the same, but then and plus, so it does more. So you run the squared residuals on the regressors and the regressors squared. So you run the residuals squared on X, and x squared. Okay, so if you have x1 and x2, then you have the squared residuals on the right hand side. You will have x1, x2, x1 squared, x2 squared, and then you multiply these x1 times x2, and so it's really and so on. So you have like pairwise cross product term of each regressor. Okay, so it actually does more than just regressing the residual square on the regressors. It actually adds the, as I said, the square terms of these regressors plus also the pairwise cross product term of each regressor. And then what we need from this new regression, we need r squared. Okay, so we obtain r squared from this regression, and to calculate the test statistic, we multiply r squared with the number of observations. Okay, so the test statistic in this case is r squared times the number of observations. What is our null hypothesis? It's the same. Homoscedastic errors. Okay, and this follow chi-square distribution. So in case if you want to use the table to get the critical value, then you need to go to the chi-squared. And the degrees of freedom here equal the number of coefficients estimated. So it depends really. So you need to count how many coefficients you have. So in that case, we did this. Sorry, yeah. So I did this very quickly. I think I didn't show it in eViews because it's very straightforward. All what you need to do is just to go here from view, and then you go to residual diagnostics, and then heteroskedasticity test, and just rather than choosing Brush-Biggin Goodfried test, then you just choose white test. Okay, and then it would ask you about how many terms you want to include or what you want to include, so give you more options to do the test. Once you do that, then you go again. You can either rely on the test statistic, which again the test statistic with white test is just r squared times what? You multiply by what? Number of observations. Yes, thank you. So number of observations, and it follows chi-square distribution. So if the test statistic greater than the critical value, what is the decision? You reject or not reject? You reject. So you reject the null hypothesis, and then the conclusion is we have heteroskedasticity. Okay. If I couldn't reject, then I don't have heteroskedasticity. Okay. So now we know what is heteroskedasticity, what causes heteroskedasticity, how to find out, how to test for, or what is the implication of heteroskedasticity. That's very important to understand how it affects all-less estimation. So all-less estimation will be unbiased, but it's not blue, but it's not best. So it will be less efficient. Your T ratio or T statistic will be less reliable, etc. Okay. So these are the consequences of heteroskedasticity. How to detect or how to test for heteroskedasticity? You could do something informal by plotting your residuals against your residual square against the y hat, and I'll show you how to do that in eViews. So that's something very informal, but you still need to confirm that using a statistical test. As I said, there's like a list of a long list of tests that you could use, but then we actually focus on only two tests: the Brush-Biggin Goodfried test and white test. Both tests have the same null hypothesis. Okay, so your null hypothesis is homoscedastic errors or errors with constant variance, which is great. That's what we want. Well, that's what we'd love to have. Okay, and in both cases, you have a test statistic and critical value. Of your test statistic greater than the critical value, then you reject the null hypothesis. Okay, concluding that heteroskedasticity is present. So you have heteroskedasticity. Okay, so the difference is the steps or how the tests work. With Brush-Biggin Goodfried test, what you do, you actually run a regression of the residual square on the regressors, on your x's. Okay, and then you use the F statistic from this regression. With white test, you actually do more than that. So you run a regression of the residual square on x's, but you actually add also. So this is exactly the same like Bush-Bacon test. You run the residual square on x's, but then you add also x squared. So you have x1 squared, x2 squared, and also x1 multiplied by x2, etc. Okay? And in that case, you use r squared from this regression, multiply this by number of observations that give you the test statistic, and you just make the decision based in the same way. And in both ways, when you do it in e-views, actually, in whatever the way you do it, like Bush-Bacon test or White test, it gives you the p-value. So that's good news. So if you have some results with p-value of that test, you just need to look at the p-value. So if you have a small p-value, you compare this with 5% or 10%, depending on significance level, really what you want to use. But usually if we look at 5%, if you have a smaller p-value than 5%, then you reject the null hypothesis. That means you have heteroskedasticity. If you have a large p-value, then you cannot reject the null hypothesis. Then that means heteroskedasticity does not exist. So now let's say now we understand all of that. So we understand what heteroskedasticity is, how to deal with it, the consequences, the causes, all these lovely things. We know how to test for it. Now we have heteroskedasticity. What should we do? I already mentioned that in the beginning. So we could use the weighted least square. So this is a method where if we know the structure of the variance, so if we know, for example, that the variance, if the variance, let's say, equals sigma squared, which is the constant, multiplied by something, okay, then if I divide by this, then it will actually cancel out and it will change the variance to become constant. So that's why it's called weighted least square. So with weighted least squares, you actually divide your observation with the heteroskedastic sigma I, and then you estimate the model using OLS. That's called weighted least square because at the end of the day, you actually divide by. But remember, in most cases, we don't know that. Okay, so we don't know. So, but in case of if you know the structure of the variance of your variance, then yeah. What's the time? Sorry. Oh, sorry. It's just I'll finish in 1 minute. Sorry. I didn't feel the time. Okay, we nearly there. Okay, so I'm concluding. Sorry. Okay. Okay, so we nearly there. So anyway, so what you could do actually, you could do the something called White's heteroskedasticity consistent standard errors, and these it corrects the standard errors. Okay, and hopefully you'll see this in the lab when you do the some examples. So when you use White heteroskedasticity consistent standard errors, or what we usually call robust standard errors. So it actually corrects the standard errors. So you will have the same estimation. So your estimated coefficients are not going to change. What is going to change is your standard errors. Okay? Remember, our issue is with the variance. Okay? So that's why when you correct for heteroskedasticity, what will change in your estimation is not the estimated coefficient. What will change is your standard errors. Okay? It will correct your standard errors just to take heteroskedasticity into account. So that's everything we want to cover today. Next lecture, we'll talk about autocorrelation and model specification. Do you have any questions? Any questions? Okay. Thank you. I'll see you next week.